So welcome everybody and welcome back. Hope you had a good start of the week and actually getting close to the weekend. And what I wanted to quickly now in the beginning, just to remind you of some of the technicalities. So this is the official website, and you can find all links relevant for the course here. You have the schedule. For those of you who are not familiar with the University of Oslo setup, you can actually go into schedule and then you can subscribe and get either a text or an email in case there are changes to the schedule. And typically after the lecture, I always upload the video, the whiteboard notes and everything. So you can always look things up again there. So you typically get a message. Now, in here on the official website, you have the login to Canvas, you have the messages, which you will also find in Canvas, and you get this as a weekly email. Everybody's registered to the course. So if you haven't gotten this email, there may be something with your Canvas setup. And the same information is in Canvas. So you have 3 sources of information here. So a triplication of everything. And the GitHub address is the one which is here, where you have all the course material, link to weekly lectures, etc. And if you then move on to the course here, to the GitHub address, this is essentially where you find all the information. And you have a weekly schedule, or the public domain here, or the pub. This is the published stuff. This is where you will find typically the weekly lectures, either as a Jupyter notebook, which is one of the formats I use, or as a PDF. So I often tend to switch a little bit between the PDF and the Jupyter notebook because we also run codes. And the other thing is, which I often use, is the whiteboard. And you will find typically the whiteboard notes. These are uploaded here after the lecture. So 2026 is the year we are supposed to use, and you will find typically the lectures for the different weeks. Okay? So that's basically the handwritten notes. So what I want to do now is quickly to switch over to the schedule for this week. So in the back there, can you see well? Is it big enough? Good. So what we are going to look at today, after a repetition of what we did last week and some of the templates in Python and C++. So you do have templates, and I know that many of you would like to write in Python, but you can also, if you prefer C++, there is a template there as well. And we can obviously help you with all these things. Actually, I also recommend strongly, when you're developing software, in case you have errors and bugs and so on, you have tools like Claude Code and Tropic, which is a fantastic tool to find errors in your codes. You can also ask it to improve it in case you want to object-orient your program, and so on. So Anthropic Claude is much better than ChatGPT when it comes to programming. And these are tools which I strongly recommend using. So obviously you have to understand the basics, but these are very helpful tools, in particular when you're doing debugging of your program. And it's so easy to make an error. Just ask me. I've wasted weeks on stupid errors where I've just interchanged indices or not declared variables properly, and so on. So using these tools is something which I strongly recommend. And obviously, when you write the report, you should also state whether you've used this beyond just debugging and developing a framework. Again, the textbooks which I'm following somewhat, there's a textbook by Hammond, Lester, and Reynolds on Monte Carlo methods. This is actually a pretty good one. And since this is out of print, you have access to that one in this Google Docs link. Then we have the textbook of Sandro Sorella, which is was actually, unfortunately, he passed away. He was a good friend, actually. And he passed away in some years ago. And he is one who has developed many of these more advanced Monte Carlo algorithms, like the stochastic reconfiguration. There is a template in C++, which I invite you to look at. And then there is also Python template. Now, in the lectures, as I said last time, I'm going to use Python because it allows me for quick visualizations and also to discuss some of the basic elements. So what I wanted to remind you a little bit about is the basic Monte Carlo, which we discussed last week. And today, we are actually going to dive into the Metropolis algorithm. So I know that some of you have seen the derivation of it, but I know that also many of you have not. So who has never seen the derivation of the Metropolis algorithm? That's a central algorithm. So we are going to spend some time today to actually go through the Metropolis algorithm and discuss Markov chain Monte Carlo methods, okay? And this is an essential because last week, when I threw at you the Monte Carlo program, where we did the sampling and used the Metropolis algorithms to reject or accept a proposed move, then we just used it without having defined to you and derived it to you. So now we're going to look at how you can derive the algorithm from the theory of Markov chains. So what we are essentially doing is that we are calculating a multidimensional integral where we have a trial wave function. And this trial wave function is the one which we are going to make guesses of in project 2 as a continuation of project 1. Many people here have actually opted for replacing the trial wave function with a neural network. And that is an extremely efficient method for actually calculating the energies with a very high precision. The first part of the course deals actually with a Monte Carlo evaluation, a stochastic evaluation of this integral. So you could say that from an overarching point of view, this is actually what we are doing. We are calculating a multidimensional integral with stochastic methods. This means that we have to be able to estimate the errors. We have to have a correct estimate of things like the standard deviation, which would be the error in the calculations. And this leads us also to resampling techniques. We are also going to look at more intelligent ways of doing the sampling, and that leads to what's called importance sampling. So these are some of the basic topics which we are dealing with. And the trial wave function, if you now have a trial wave function which can be expanded in the exact solutions, then we have the famous variational theorem, which simply states that if you now would have the exact wave function, psi0 here, the exact one, if this psi t is equal to psi0, only that one, only one coefficient, then you have the exact ground state energy. So a Monte Carlo method, in the way we are going to deal with it, is a method which uses the variational principle. It means then that what you will be targeting is the lowest lying state with a given symmetry. Now you can have excited states with different symmetries, representing different quantum numbers. So if you're then targeting specific symmetries, so if you tailor that in the wave function, then you can also target excited states, and you will always get the lowest lying state with a specific symmetry. Now, the Hamiltonian is normally an object which has some specific symmetries. So we are going to have a rotational symmetry. You can have translational symmetries. So these are invariances which are kept in the Hamiltonian. And that means that it will target, the Monte Carlo method targets the state which has essentially the same symmetries of the Hamiltonian as the lowest lying state. These are things which you can prove. We are not going to do that. We're simply going to state it. Okay. So the variational principle is what we did last time. We derived it, and that gives us a kind of benchmark of what we can obtain. But as I say, the tedious part in a variational Monte Carlo calculation is the search for the variational minimum. So that means a good knowledge of the system is normally required in order to carry out the reasonable variational Monte Carlo calculations. You could obviously start with any function, but it doesn't mean that it will give you a meaningful result. One quantity, so since we don't know the lowest energy, it means that you typically end up trying different functions, trial functions. So this t, which you see here, stands for a trial wave function. Now, one number, however, which we know exactly, if you have the exact wave function, is the variance. So if you have the exact wave function, as we discussed last week, then the variance is exactly equal to 0. So many practitioners have also tried to run the variational calculation by varying both the variance and the energy. But the variance leads to many more integrals to evaluate because the variance is connected with the second derivative of the energy expectation value as a function of these variational parameters. And second derivatives leads to many more integrals. We will, when we do the optimization part, which is also a central part, and many of you who've taken a course in machine learning, you know that at the heart of all machine learning algorithms, there is an optimization part. And the optimization part means that we are going to, and that is where we are going to plug in a lot of labor, is to calculate the gradient of the energy as a function of these parameters alpha, which are the variational parameters. So we are coming back to that. So there is an optimization. In the beginning here, we are just going to run things in a brute force way. So we are simply going to run calculations with different parameters. And we are going to plot the energy as a function of these parameters. And then by the eye, we're going to say that, the minimum is there. But then we are not going to be satisfied with that brute force approach. So we are going to introduce more refined approaches, which then leads to numerical estimations of the minimum by calculating the gradients. Okay, so this is roughly the kind of overarching picture of what we are going to do. Yeah?
I thought you said you're... Oh, okay, sorry. No, are we first like making a graph of the energy?
Yeah. So we, in the beginning, before we have gone into how to run the optimization of the energy, because suppose now you run 1 million Monte Carlo cycles for every value of alpha. And clearly, if you have two parameters and you have typically 10 parameters for each, then you get 100 parameters. And each calculation with 1 million Monte Carlo cycles is going to be expensive. So that's what we will call the brute force approach, which we will do in the beginning. And then we are just going to localize the minimum by the eye, as it's called. But then we are going to look at the more efficient ways of doing that. And that means that we will have to calculate the gradient of that expectation value as a function of the parameters. Then we are going to use few Monte Carlo cycles to find the minimum. When we have found the minimum, that's when we will start the big machinery and run through many Monte Carlo cycles. So the number of samplings, the more you can do, the better it is. Because we believe in the Bernoulli's law of large numbers, which says that the larger amount of samples you have, the closer you get to the true expectation value. So these are the kind of rough guidelines for what we end up doing here. So the tool which we will have for doing the sampling is, so the sampling itself is the Monte Carlo machinery, where we pick points randomly, but then we have a selection rule. And the selection rule for accepting or rejecting a proposed move is given by the Metropolis algorithm. And that's what we need to discuss today. So here is a kind of bird's eye view on what we are doing. You would then construct a trial wave function from a many-body system consisting of n particles located at different positions. And then you have a trial wave function, which depends on these parameters. You evaluate the expectation value. Thereafter, you vary this alpha according to some minimization algorithm, and then you return to the first step. And this is the basic procedure here. And then what we did last time, so this is still a repetition of what we did last time. What we did in order to rewrite that integral as a standard statistical expectation value, we then rewrote the integral in terms of what we call the probability here, which is this is just a quantum mechanical probability. And then we defined what we call the local energy. And with the local energy then, we could rewrite the integral as a probability times the local energy. And then when you do the Monte Carlo sampling, this is just 1 over n, where this n is the number of Monte Carlo cycles. And then you pick these points randomly, and then you simply accumulate as many as you can. And obviously, the ideal is to have as many Monte Carlo cycles as possible. But if you have many particles, you quickly see that the computational expenditure in terms of CPU cycles or GPU cycles increases dramatically. So if you're moving 100 particles, so in the evaluation of these integrals, there are different algorithms which we can choose when we move the particles. So we can move one particle at a time and test whether we accept that move or not. Or you could move all particles and then ask whether you want to accept this as a suggested move or not. For those of you who took a course in computational physics 1, you probably simulated the easy model. Has anyone simulated? And then what you did then was to flip one spin at a time. You could obviously flip all spins and then perform the metropolis test. But the reason why you typically flipped one spin is that is more efficient computationally than flipping all spins. And you will see that for some specific systems here, it can be more efficient to flip or move one particle at a time instead of moving all particles and performing the metropolis test. So these are things which we are coming back to. So basically the algorithm, which we went through last time, was simply to fix the number of Monte Carlo steps. So that's a parameter you fix. So this is the Monte Carlo algorithm. And then you choose an initial position, and then you have a loop of variation parameters. You initialize the energy, then you calculate a trial position. And what we discussed last week was a way of moving the particles without thinking about the probability which governs the system. So this is normally called a brute force move, in the sense that we just let the particles move irrespective of what the probability distribution looks like. Later, we are going to look at importance sampling. Then we have the metropolis test, which is just a ratio between the probabilities, new position divided by the old one. This is the metropolis test. So, or metropolis algorithm. So the Monte Carlo algorithm is actually everything here. But then whether you accept a move or not is given by a sampling algorithm, which is called the metropolis algorithm. We have many other ways of doing this. There's something which is called Gibbs sampling. There is also something which is called Langevin sampling, and many other ones. But the metropolis one is the method of choice because it's easy to implement and it's fast numerically. Gibbs sampling is also another possibility. If the step is accepted, you set the new position to the suggested one, and then you keep moving and update averages, and finally you compute the final averages. So last week, we actually looked at the harmonic oscillator, where we had a trial wave function, which is then motivated by the analytical expression for the ground state. And this parameter alpha became the variational parameter. So when it comes to the project, the thing which we want to do first is actually to calculate the local energy of one particle, which is the expression you see here. And then you're going to do that for more particles. And we are going to look at the non-interacting system, because then we know the exact wave function. So for many particles, the exact wave function is actually given by a product of the single particle wave functions, because there is no interaction. So no types of correlations between the particles. These are just independent and identical particles and no interaction. So that means that the wave function, the exact one, is just a product of the single particle wave functions. And that means that when you then are calculating this local energy for n particles, you need to add this for n particles. So we want you to do that in this. Or something. Let me just move this one. Okay, went fine. So what we need to do is actually to evaluate these analytical expressions for the local energies. Now, for the harmonic oscillator, then you have, sorry, this actually disappeared a little bit, but if you look it into yourself, it shouldn't be like this. Something with the rendering on the screen here. But then you have an analytical expression. And for n particles, I mean, it's just n times this expression. So that's a very nice way to build up your program by running it for the non-interacting case. And we are going to add all the different elements for the non-interacting case. And then at the end, we plug in an interaction between the particles. And then we have a final, almost professional looking variational Monte Carlo program. And you can also calculate the variance. We have an analytical expression for that because we can integrate these function here analytically. So these are just the analytical results. And in the program, and now we are going to dive into the Monte Carlo Markov chain machinery or Markov chain theory. And what we did then was first to establish the expressions for the wave function. We have the expressions for the local energy, those analytical expressions you saw. Normally, you would have to calculate the kinetic energy in one way or the other. So here we have a simple, nice analytical expression. So here I'm now just setting up the wave function and the local energy. And the Monte Carlo machinery here, with a given number of cycles, I have a step size. I'm initializing two arrays, position old, position new. I'm running over variational parameters because I know that the minimum, as we discussed last time, is at the alpha equal to 1 for that trial wave function. And then we have a loop here over the variational parameters. We set up a new position since this is a one-dimensional problem. So if you're doing this in 2 dimensions and 3 dimensions, you also have analytical results. But then you will need to set up the position for X, Y, and Z if you're doing 3 dimensions. And in this case, we are just, since we have an integral which goes from minus infinity to plus infinity, by doing a random number with a uniform distribution between 0 and 1, and subtracting 0.5, we get positive and negative numbers. And then the Monte Carlo cycle, so this is the Monte Carlo algorithm. We suggest a new position, old position plus the new step size. We calculate a new wave function, and this is the metropolis test which we're going to derive today. With that, with a new position, we calculate then the new contribution to the local energy, which is actually, if you go up a little bit, it's actually this contribution here. This is one of the many ones which you're going to sample. And then you keep adding these. And when you keep adding these, at the end, you calculate the energy and the energy squared because you want the variance. And the final result is just simply the energy you have summed up divided by the number of Monte Carlo cycles. So this is your expectation value. And then you also, here we can calculate the variance. And then we calculate the standard deviation, which is the square root of the variance divided by the number of Monte Carlo cycles. And just run through this one. And in this case, we do 20 variations, calculate the energies, compare with the exact energies and the exact variances, and then we just plot. And as we saw last time, we got something which looks like this. So the minimum is at 1.0. The minimum should be 0.5 in this dimensionless units. And you see that the variance at the minimum is exactly equal to 0. And if you look at the results here, you see now for this 0.1, then you have an exact energy, 0.5, to the number of digits we have here. And all the other energies are higher than that one. And the variances, as you can also see, is exactly equal to 0 when you have the exact parameter alpha. So this is basically the Monte Carlo machinery in a nutshell. And in the beginning, you could actually take that program, which you see here, and make modification to it so that you can run calculations in 1, 2, and 3 dimensions with 1, 2, 3, or many particles. And you have analytical expressions. For the local energy, And the wave function is pretty simple. So this is the first task, the first step, which we want you to develop within the next 1 to 2 weeks. And then next week, we are going to add importance sampling, which is a better way of sampling the points. And then we gradually bring in more and more elements, but we still do all the calculations with a non-interacting case, because we have a simple local energy and we have a simple wave function. Okay, so that's roughly, this is a kind of repetition of what we did last time. And if we now look at the Markov chain here, why do we use Markov chains? So a Markov chain, I should also say, there are some very, from an overarching point of view, if you think of Schrödinger's equation, if you translate that one into imaginary time, Schrödinger's equation is a diffusion equation in imaginary time. So it's very easy if you just translate t to I times tau, complex time, then you're not solving Schrödinger's equation anymore. The spatial degrees of freedom stay the same, but time is now imaginary time. But then in the limit where time goes to infinity, you can actually show that that brings you to the ground state of the system. So Schrödinger's equation can be solved as a diffusion problem in complex time. Now, a diffusion process is intimately linked with Markov chains. You can derive, and I don't know if you've seen this, but you can derive the diffusion equation from a Markov chain process. So these are very intimately linked expressions or approaches to the same physical mechanism of diffusion. So if you now go back to the wave function which we had, so this simple model here, we have a wave function which is going to look like this. And if you have many particles, this is just simply going to be x1 squared, x2 squared, x3 squared, etc. But you see quickly then that this probability distribution becomes pretty big. Yeah, that's Google and Meta and so on, which are following with us. So in case you say something nasty about Trump, then you are just registered immediately. So this will be recorded, actually. It'll be on YouTube. So I will have problems when I get back to the US. Sorry. I couldn't resist. So these are the kind of things which are taboos to make political statements, religion, sex, and race when you teach. But I couldn't resist. Sorry, I hope nobody gets angry with me for that. But the thing with a Markov chain and why this is so interesting is one, you want to study a physical system which evolves towards equilibrium. So what does it mean? Equilibrium means a steady state. And when we do the Monte Carlo sampling, what we typically can show is that you can, after some samples, you reach the most likely state the system has, which in our case is obviously the most likely state with these parameters alpha. Then when you have reached that, after some initial random jumping, then the system remains roughly in that state. And then you're sampling in and out of that state. So you just think of you having a box which has a wall which divides the box in two. And then you have a gas of molecules in this box. And then you open up a hole. And then the particles will drift back and forth. Till the end, you have roughly half the particles in the left and half in the right box, if you don't have any bias towards left and right. Now, this is the equilibrium situation. And when you then are going to sample events from that equilibrium situation, you will actually sample around that one. So particles will jump in and out. But it stays roughly with half the particles in the left container and half in the right container. So when you start with a PDF, you want to understand how the system evolves with time. And you want to reach a situation where after a given number of time steps, you obtain what's called a steady state. This means that the system has reached this most likely state. Now, this is ideally what you're doing with a Markov chain. And our PDF, probability distribution, is normally a multi-dimensional object. And if you think of the quantum mechanical wave function, one of the tricky things is you evaluating the normalization constant. If you have 10 particles in 3 dimensions, your integral for the normalization constant is a 30-dimensional integral. And clearly that's a pretty difficult task to evaluate properly. So you see all these problems, you might actually think this is not possible to do, right? And then the other thing, even if you have an analytical calculation, so this W is the probability distribution, even if you have an analytical expression, it can actually be difficult to sample from it because it's such a high-dimensional object that it requires many CPU cycles. So as I say here, to sample directly from the probability is not always possible, or it's actually difficult. And the transition to a given state is normally also not known. So this sounds really impossible, okay? But let's see how we can do that with the theory of Markov chains and how we can find in a smart way an algorithm which tells us if we can accept a move or not. So I'm going to switch over to the whiteboard now, and we are going to look a little bit at the theory of Markov chain theories. So there's a lot of information here, but take a look at it. We're not going to go through everything, but I wanted to highlight some of the basic things here. So I'm just going to use a generic representation of the probability, and I'm going to make life a little bit simpler. So I'm going to define a probability distribution, PDF, which I will just label with a lowercase w. And this represents the probability of being in a position X at a time t. So this is the way you would read a probability distribution. In our case, what we have is that this Wx of t is replaced by the quantum mechanical distribution with R and a parameter alpha. So I'm not going to use this notation here because that becomes a little bit too wieldy with a, so we have alpha of these parameters, this is squared, divided by the integral over R and then psi of t, and I'm skipping that one. So I'm just going to use this W to indicate that we have a probability distribution, which is known. And what we want is that we start with an initial state, X, and then we have time equals 0. And we want to see how this evolves to the steady state at time in principle infinite, at long, long times afterwards. So this is our steady state. So the probability distribution is the one which now represents the most likely state of the system. Okay, this is roughly what a Markov chain is going to simulate for us. So let's now look at the mathematical definition of a Markov chain and bring in some of the basic components. So a Markov chain is a chain of events where the new step depends only on the previous step. But we can obviously step ourselves backward. So what I'm going to have now is to define a probability for being in a state. Probability for being in a given state, I. So I'm now replacing this X, the position, with a state. So you can think of being in a position X as you being in some state. So X can represent the spatial degrees of freedom, it can represent spin, or some other quantity. So what I'm just going to do now is simply to write this probability as a Wi of t. And then after a step which I will label as an epsilon. Then I have a new probability, which is now given by the sum over all the possible states the system can be in. And then we have something which is going to be labeled as a transition probability multiplied with the probability of being in this state J at the time t, at the previous time. This is essentially the mathematical definition of a Markov chain. This quantity here is normally called a transition probability. And in essentially all the situations, it is unknown, except for some simpler academic cases. Now, in some cases, you can actually calculate that one. If you think of, so I know that some of you are more familiar with atomic physics and molecular physics. If you think of the hydrogen atom, and if the system is in an excited state, we can often calculate analytically the expression for making a transition from the excited state to the ground state. So that would be an example of where you have an analytical expression for the transition probability. So then you would multiply that one with the initial state, and that would bring you into the new state at the time t plus epsilon. Whatever this epsilon is, depends on the type of system you're looking at, okay? So this is the basics of the Markov chain. And you see now that the new state depends only on the previous state. Now, this quantity here, and I'm going to mark this with red, this quantity here is in general unknown. Unless you have a very simple case, like suppose now that you are jumping left and right in one dimension. So you would have x0, you have x0 plus 1, you have x0 minus 1, and then you could think of you jumping along this line here. You would start here, and then you can jump left, or you can jump right. And then you can say that if this is very democratic, you can say that there is the same probability of jumping left and right. So what you could say then is that you could define a probability distribution, W, this is the Wij, which you could say that this one is equal to 1/2 if the distance I minus j is equal to 1, the absolute value, or 0 else. In that case, you know the probability. So it's just a half. Actually, this expression or this kind of simpler probability is the one which you will find in many textbooks when people start with a Markov chain and then derive the expressions for the diffusion equation, the partial differential equation. You can actually derive that one starting with these ansatz for the probability, for the jumping probability or the transition probability. Okay? So this is a case where you know it. But in general, we have a problem which is so complex and complicated that there is no way we can actually find a practical expression for the probability distribution. Either we don't know it or the expression is too complicated. So this sounds like mission impossible, right? But this is where the Metropolis algorithm kicks in and helps and saves the day for us. So let's look at how we can move from this equation and derive the Metropolis algorithm, which is a way to actually simulate this process without knowing this one. Now, the thing which we have in our calculations is that we do have a model for the probability. So when we are setting up the trial wave function, we do have a model here. So this is going to be the trial wave function. So it means that we can actually calculate this quantity here. However, this quantity here is a quantity which we would have to simulate with a Metropolis algorithm. So let me try to show you how we can actually get there. So first of all, I wanted actually to say a little bit about this matrix W, So I'm representing everything as matrices. You can translate everything you do here into an integral equation. But I find it often more convenient to just use a matrix vector representation, if that's. So let's take a look at the quantities which we need to look at. So this quantity Wij, that is an element of a stochastic matrix. Which we simply label as W here. Now, these matrix elements, this is a stochastic matrix elements, there are conditions on these quantities Wi. So these Wij's, they have to be less or equal than 1 and larger than or equal to 0. When I sum the elements of the column elements, Wij, they sum to 1. So this is a normalization constant. So as an example, consider this matrix here, which is actually a stochastic matrix, 1/2, 1 divided by 4, 1 divided by 4. I can have 0, 0, 1, and then I can have 1/3, 1/3, and 1/3. And you see now that this every column element sums to 1. So probably when you took a course in linear algebra, they talked about stochastic matrices. There is another important property here, and that is that the eigenvalues of this matrix W, they are less or equal than 1. Okay, that's a very important aspect. And you will see that if you diagonalize this one, this has the largest eigenvalue equal to 1. And that is the one which corresponds to the steady state of the system. The state to which the system evolves after some steps. Now, that was the probability transition or transition probability. But then we also have the probability itself, W of I. This is something which is also respecting all the properties of a probability, and it's also normalized to 1. So when you start with an initial probability, then it's actually something which then depends on these properties which we have defined here. Now, there's also another basic assumption here, which we are going to make, and we are going to make now an assumption. You can actually break this assumption, but in the derivations here, we are going to assume that the matrix T is time independent. Now, if I then look at the probability Wi, and now I set T equals 0, so I look at epsilon, so I start with T equal to 0, then this is equal to J, and now I'm just going to write this in a slightly different way. So I write it as the probability of making the transition from J to I, because then instead of just writing this as a matrix with subscripts, I'm now explicitly saying that I'm jumping from a state J to a state I. So previously I wrote it like a matrix, as you see here, with a specific matrix element, but now I just want to use this notation because that is in essentially what we are doing when we simulate this in a Monte Carlo process. We're actually going to jump from one state to another state. So I just wanted to have this kind of notation here when we move on. You can easily translate this back to just the standard matrix notation. So this is start with a J, and now we are starting with T equal to 0. And then you see now that if I look at this state, and if I use a matrix notation, a vector notation, I can actually write this as a W times W0. And then you see now that the next state of 2 epsilon, I made 2 time steps, is actually the same as W times W1, which is the same as W times W0. And then I can do this many, many times. So I can have n times epsilon, and this would be the same as the matrix W times n times W0. Now, after the break, we are going to look at what this means practically for us and why this process here is going to converge to the state which has the largest eigenvalue. And the largest eigenvalue is equal to 1. But now we need a small break. Is that okay? So let's do that first then. So what I want to do now is to show you what happens mathematically when we are moving towards the steady state or the most likely state of the system. So if you now look at the expressions which we put up here, this way of representing the Markov chain, having assumed that this W is time independent, then we can actually start with the distribution at the initial time. And then by repeated operations with this transition probability, we are getting to a new distribution after n steps. And this is n times this epsilon, which we later going just to put to 1 for simplicity. So you can think of that as a kind of scaled time step. So one thing which we should also keep in mind now, since we have called this a stochastic matrix, that has eigenpairs which we are going to label with a lambda of I and a vector v of I. So v of I is the eigenvector. So what it means is that when W is now acting on a state v of I, this is the same as lambda of I of v of I. Now, the v of i's construct then a basis, which we can obviously make orthogonal and normalize. So that means that what we could do now is to take the distribution at time t equal to 0, and we could expand that one in this eigenbasis of the matrix W. So that means that since this v of I defines a complete basis, there is an overlap coefficient alpha of I, and then we have an expansion in terms of the eigenbasis. So this is something which I'm assuming you're pretty familiar with from linear algebra, which means now that if I act on this state with the matrix W, then this is simply going to be given by I times alpha I of W of V of I, which translates into I of alpha of I, multiplied with lambda of I of V of I. Then, if I now look at the same expression after n steps, this is simply going to be given by my W of n, and now I just put for simplicity this epsilon to 1, just to make life easier. This is just a parameter which we can scale as we want. And this is the same as I of alpha I, but now I get lambda I to the power of n, multiplied with V of I. So what we also have defined, so this is a stochastic matrix, it means that the eigenvalues of this stochastic matrix are less or equal than 1. And now we can sort them so that we have a lambda 0, the first one, which is larger than lambda 1, which is larger than lambda 2, and so on till the final one, which is lambda of n. So we're assuming now that we have a set of eigenstates, and lambda 0 is the one which we label as or define as the largest one. And in a stochastic matrix, it means then that the lambda 0, the largest one, should be equal to 1. And you will see that if you diagonalize a stochastic matrix. So what that means, if we look at the sum which we put up here, this sum here, I'm going to define a new parameter, which I'm just going to call a tau of I, which I label as a -1 divided by log of lambda of I. So then it means that I can write this probability distribution after n steps as a sum over I equals 0 up, and in principle, this goes to infinity. So in principle, the matrix is infinite dimensional, but we will always truncate somewhere. So we would have an alpha of I, and then we have the vector V of I, and then we have E to the power of -n divided by this tau of I. This is just a plain rewrite of what we did. Okay? And then what we have done now is that this time, which we are dealing with here, this was originally what we called the time, which was n times this epsilon. So you can think of this n here as something which is reflects a given set of time steps. Now, if you now look at this one, we can obviously rewrite that one in terms of an alpha 0 times V0 plus the remaining terms, I equal 1, and then we have alpha of I of V of I of E minus T divided by this tau of I, where we now have replaced time, no, sorry, n. I want to have n here, like that. So this n, you could think of that one as a number of time steps which we've been doing. Now, the thing which we know is that this eigenvalue, lambda of I, for all the other states, is always less than 1. And then, depending on how fast this is actually moving, you see now that lim of n goes to infinity of Wn is actually equal to alpha 0 times V0. So how fast it goes to this specific state depends on the values of the eigenvalues. So if the second eigenvalue is pretty close to 1, then clearly the convergence will be slower. If the eigenvalues are typically 1 for the largest one, and then the other ones are 0.5 or even smaller, then this will converge rather quickly to that state. So what is happening now is that the process converges to the steady state. And there is no dependence anymore on time here, if you think of n as a kind of time. So in the limit, where this process now is going through infinite many time steps, you have actually reached what is called the most likely state. So we would call this one here for the most likely state of the system. So this is the most likely state, or the steady state. And or the equilibrium state. It's normally called steady state, the most likely state, or the equilibrium state. And this is a situation which a Markov chain moves towards. And you can see that from another point of view, because what happens then is that if we look at the Markov chain, then when the system has reached equilibrium, then what happens is that the state W of n is equal to the matrix times W of n. So this is in the limit Markov chain. In the limit, so this is the steady state. That means when n goes to infinity. And then you can read off this one immediately as an eigenvalue problem. And you see now that you have a matrix times a vector, which is this W. And this is equal to a vector. So then if you read off, then you see that the eigenvalue is equal to 1. So you can, if you go into the lecture notes, you will find an example of a 4x4 matrix where we simply start with a random initial value and see how that converges to the steady state. And you will see that that specific state, that specific eigenvector, is the one which corresponds to the eigenvalue equal to 1. So what happens then, when you look at these expressions, is that in the limit, when n goes to infinity, we can actually replace these equations with w of n goes over to w, and that is equal to w here, and that is the steady state situation. So the process is no longer time dependent. So this is an important property of the Markov chains here. Now, what we can do now, if we now go back, because we said that we don't know how to model this quantity here. We don't know that. And this is the steps which we want to introduce now when we look at this Wi of a state t, at a time t, we wrote this in terms of a j, and then we have this transition probability from j to I multiplied with us being at a state j, and now I'm going to replace this with some time t minus 1, just for simplicity. Instead of having epsilon, having t plus epsilon or t minus epsilon, I just define the steps to be equal to 1. Now, the problem which we face is that this quantity here is normally unknown. So in all our simulations, we have made a model for the probability distribution, which is our wave function squared. And that means now that we need to find a way to model this quantity here. So what we want to do then, since we are going to make a model, we can model it as we want, okay? So what I'm going to say now is that this w of j of t, or j to I, is something which I will model into two probabilities. So w is a probability of making a jump from a state j to a state I. So if you think of this simple case, we're jumping left and right, we put that probability to 50% left, 50% right. And then we are now going to model this in terms of two probabilities. And this probability here is something which we will call the probability of accepting a move. So what I'm saying now is that we don't know this quantity w. So we can make an approximation to this quantity w. And this is what we're doing now. So when you don't know something, in a certain sense, you're free to model it as you want. Obviously, you model it according to your insights. So this is the probability of accepting a move. So I make a suggestion of making a move, and then I'm multiplying my probability of making. So this is the probability of making the transition. But then I'm saying that I may not accept this move. So I'm just splitting my probability. And this is a probability of making the transition. Probability of making a transition. And later we will look at approximations to that one. So the standard metropolis algorithm normally assumes that this process is reversible. And you will see that in the equation then, we are just going to look at ratios between acceptance probabilities. That is the simple metropolis algorithm, which is often called the plane of the brute force metropolis. Then, when we are going to introduce importance sampling, we are going to make a model for this probability t, which then will improve the way we do the sampling, because the random walkers will then just jump according to a given probability. So, as I said, we are free to make a model. And this is actually what people did when they invented the metropolis algorithm. So the thing we also need to say something about is also that these are probabilities. So it means that all the elements here, so this is a specific element of the matrix T, is less than equal than 1. And same with A. So you can think of having a matrix T and J, and they have elements. So in principle, I should have written this as a Tij, and this would be an Aij. But I want to keep this notation because we are now just looking at, I think it's a more physical intuitive to look at that specific notation than having just subscripts of a matrix. Because now we are explicitly stating that we are making a transition. Now, what I'm going to do now is to rewrite the Markov chain. So I have a Wi of T. This is my Markov chain. So J, and then Wj going to I, and Wj at a time T minus 1. What I'm going to do now is just to manipulate this expression with these terms, and I'm going to rewrite this in terms of two terms. So I'm going now to say that if I accept J, so I accept this move J with a probability A. So if I go from I to J, I'm actually accepting that move with that specific probability. But then I also have a probability of rejecting. So and then the probability is actually has to be given by 1 minus A of I going to J. So if the probability of accepting is given by this quantity, then since we have to sum the probabilities to 1, then clearly the probability of rejection must be given by, so I should have an N here, sorry. So that means that I can rewrite the equation which I had for the Markov chain in a slightly different way. So this is just a manipulation of the equations which we have for the Markov chain. So what I'm doing then is simply now to rewrite that probability at a time t in terms of a probability of accepting and rejecting. So I have a J, and then I have my Wj of t minus 1. This is the state I am in. And then I'm making a transition from J to I, all the possible states I am, multiplied with A of J to I. But then I'm adding to this one the probability of being in I of t minus 1, multiplied with the probability of going from I to J, but this is now multiplied with the probability of rejecting that move. So which is simply A to J, and multiplied with, no, so it should have another parenthesis here. So this is just a rewrite of the equation where I'm just manipulating probability. So this is the probability of making the transition from J to I. But then there's also the probability of going from I to J, but this has to be multiplied with rejecting it. So when equilibrium has been reached, when we reach equilibrium, reach the steady state or equilibrium or the most likely state of the system, what we have then is that Wi, as we saw from the previous analysis, must be equal to Wi of t minus 1. So these two probabilities have to be the same. Because we know that in the limit, when time goes to infinity, then the probabilities become time independent. And you will typically see that with a diffusion process. So how many of you have simulated the diffusion equation? And then you know that when you started the simulation, you had a distribution. So suppose you take a rod with a temperature distribution. And then you're looking at the diffusion equation or the heat equation, they are just the same. And then you have a distribution of temperature at a given time t. And then you put this rod, which has a temperature distribution, into a bath, or you put it into the Fjord of Oslo. And then you know that from your intuition that after some time, the rod should have the same temperature as the environment. So suppose in the beginning that the rod was warmer inside than at the endpoints, but then you know that after some time, the rod has the same temperature as the Fjord of Oslo. And that means that your function, which previously could be peaked as a function of the distance or the length of the rod, is suddenly the same everywhere. And that is your most steady state. That is the equilibrium situation, right? That sounds reasonable, right? And this is the same thing which we are doing here. Actually, the mathematics of Markov chains and the diffusion process is pretty neat. But we don't have the time to cover that in all details. So what happens then, when we do that, then we can obviously rewrite the equations which we started with. So we would then have that equation, because we can then rewrite it. So if you look at this one, there is a term here, this term, which now is just given by t, that we just take away time here. And we will rewrite this term without time. And then the same applies to this one. And we can put this outside because this doesn't have a summation of the I. Then we know that these probabilities here are summed to 1 due to the normalization. So the normalization condition, when I sum from J here, this means that this has to be normalized to 1. So what I'm getting then is the following expression. So I will have a sum where I have J, and then I have Wj. There is no time dependence anymore. And then I have my T of J going to I. And then there's a J going to I here. And this is equal because now we can bring back the other side. So this has to be equal to Wi of T of I going to J, and A multiplied with I going to J. So what happened then when you look at that specific term, so let's just single out that one. That term was originally given by J of Wi, and then we had T of I going to J, multiplied with 1 minus A of I going to J. Now, the first term sums simply to 1. So we get a Wi, because we have a probability here where we sum T of I going to J over J. That is normalized to 1. That's by definition. And then I have a term which goes like minus. And then I have a J, and I have a Wi, and A of I going to J, and T of I going to J. And you see now that this term here, which was on the right-hand side of the equation, this term cancels the term which we have here. And that gives us an equation now where we have this term, which has to be equal to that term. So the equation which we end up with when we have reached the most likely state of the system is a Wj of T of J going to I, of A of J going to I, and this is balanced by this other term of J of Wi of T of I going to J, and then A of I going to J. Now, this equation here is the equation when we have reached the most steady state. Now, what you can show is that there is something which is called a conditional balance, which guarantees. So this is some mathematics which we will not cover. The equation here is actually not that easy to implement. But if you now look at what you have inside the sums, you have if you now just take the sums here, and then you require that the difference between this part and that part inside the sum should balance, then you can mathematically show that you can avoid, if that the requirement is fulfilled, something which is called cyclic solutions. Because when you have a matrix W, where you can actually have different most likely states, then the process will not converge. But there is a mathematically a more how should we call it? It's a necessary and sufficient conditions of detail balance or condition balance, and that is our setting of Wj of T of j goes to I of A of j going to I being equal to Wi of T of I goes to j. So we're just setting an equality inside the summation signs. And this is normally called detail or condition balance. And this is the starting point for the derivation of the metropolis algorithm. So let's just frame that in here. So this is the equation which we are going to look at. Not that one, but this one. So if I take that equation and I look at the ratios now, so the next step which I'm going to do is simply to take this equation here, and I can just divide with Wi on both sides, or Wj. So I can set up the ratio of Wi divided by Wj. And this is equal to T of j of I of A of j goes to I, divided by T of I to j, and A of I goes to j. Now, the important thing for us now is the following, and that is that this ratio is known. Known, since we have a model, So even if it's a complicated model, we do have a model. Now, one thing which is nice now, if you think of the harmonic oscillator wave function, which we had, and if you think of your trial function as a product of harmonic oscillator wave functions, you would then say that if I have 100 particles, I would actually have to evaluate this for 100 particles. But if you are looking at a case with no interactions, what happens then is that the probability is just a product of the single particle wave functions. So if we then move a particle at a time, we just need to calculate the change for one particle, and all the other ones factor out. Another thing which you see, which is nice here, is that your probability, so let me just write this down so you see it in a better way here. Right? So if you now, there are two important things. So our Wi is actually equal to the quantum mechanical probability of being in a position I with a parameter alpha. And that is the quantum mechanical trial function squared, Ri, of alpha, and this is in principle a vector because we have many parameters, divided by the normalization factor. One thing, the normalization factor, for those of you who are familiar with the Ising model, you know that the normalization factor is the partition function in statistical mechanics. That is an ugly beast to evaluate. We don't want to do that. Because except for the few cases where you have, for the Ising model, spin up, spin down, if you have some few cases, you know that the number of possible distributions, if you have 100 spins, is 2 to the power of 100. forget it. You will never be able to evaluate in your lifetime or in the time of the universe the normalization constant for even that baby case. So the nice thing now is that if you look at this expression here and you put that one in this ratio, is that this quantity disappears. We don't need to evaluate. And that's already one very, very beneficial point of view for the calculations. Now, when you're setting up the wave function, there is another aspect. So suppose I have two particles, and we are doing the harmonic oscillator now. In one dimension, that means that your probability then, the P of R of I, or R of I here, of alpha, one of these probabilities would be proportional to e to the minus 1/2 alpha squared. And then we have the position in one dimension for electron 1, and this is squared. And this is multiplied with e to the minus 1/2 of alpha squared for electron 2. And now you see you can repeat that for many electrons. Now, if I have, let's say, 100 electrons or 100 particles, then clearly I would have to evaluate this one for 100 particles if I move all 100 particles. If I move one particle at a time, what happens then in this ratio is that only one of these will change. All the others stay the same. So the algorithm for performing the update, so you can obviously always move all particles at one time and then perform the ratio, or you move one at a time and calculate the ratio. And you see now from a computational point of view, if you move one particle at a time, I don't need to evaluate a complicated probability distribution. So instead of you moving 100 particles, you would actually have to evaluate that function with 100 particles. And if you have correlations between the particles, it becomes even more complicated. But moving one at a time makes this ratio much easier to compute. So these are things which deal with the computational efficiency of the algorithm. But the most beneficial aspect is us not needing to calculate the normalization constant. But then you might say, hey, what do I do with the rest here? The right-hand side, I have no idea. I can calculate a ratio, but that doesn't give me A, it doesn't give me T, right? So we are going to make a first approximation now. And then we are going now to assume that the probability of moving from J to I and to I to J is given by a unitary process. So we assume also that it's reversible. So this is an approximation we make. And this is going to simplify life because we can now say that going from I to J should have the same probability as going from J to I. So this is an assumption we make. Later, we are going to change that so that we are going to introduce a probability which is given by the quantum mechanical distribution we have chosen, and that will change the probability of moving from I to J. But now we're going to make this assumption. And then you see that everything simplifies to an easier expression, which is Wi divided by Wj is equal to a acceptance probability of going from J to I divided by the probability of the reverse process. This is the acceptance probability. But in principle, I should have kept all the rest there, right? So if I have that, then the question is, I know this ratio here, the left-hand side, I can calculate that. I am in a position J, and I make a move to position I. I have an analytical expression or an expression I can evaluate for the probability. This is our model, the trial wave function. But then I don't know anything about A. So what do you do when you don't know anything?
Yes.
Yeah, but you have some guided guesses, okay? And the guided guess is now as follows. So if you now suppose, let me see if I can trigger your intuition here, because the Metropolis algorithm is just based on this. So let's make a simple example, take a simple example. Suppose now that the probability which we have is just a plain Gaussian, okay? And it looks like this. So we are in one dimension. This is my ideal dimension. According to my wife, I'm a one-dimensional character. So as soon as I move beyond one dimension, I'm on a shaky ground. So if we now look at suppose now you start here, x0. This is a probability, it's a Gaussian. So that means at x0, we are here, and we would just call this W0. Now I make a suggested move. So my suggested move now is now me moving to x1. So I'm just jumping randomly, and that brings me here, which is W1. So W1 divided by W0 is larger than 1, right? So that sounds reasonable, right? And if you look at that one, that means that the ratio which we are looking at, so let's just put that up in the corner here. It means that my probability of moving from 0 to 1 divided by A from 1 to 0 is also has to be larger than 1. Keep in mind that you could also stay in the same place. That's another move which is fully allowed. So you're not discarding you staying in the same place. Then you would have a ratio which is equal to 1. So we could now think of looking at the case larger or equal than 1, okay? Because you could stay in the same spot. Okay, so if you look at that one, we do have some conditions on this probability. Or J to I, because A is a probability. So it has to take values if it's normalized between 0 and 1. So if we don't know anything, what could we say here about the probability of moving from 0 to 1? If you don't know anything. So you can make a model for it, obviously, but you could make something very simple. So what would you, if you look at this line here, so the maximum value is 1. Okay? That's the maximum value. So what we know then is that if this is the case, that the ratio is larger than 1, it means obviously that what is in the denominator has to be smaller than what is in the numerator, right? I hope you don't get offended if I just bring this in. So if I don't know anything, what could I then say based on this relation here? So we know that they have to be between 0 and 1. Yeah?
The other A,
yeah,
behind between 0 and A, J to I.
Yeah.
Then you have something.
Yeah. Or you could just say that you could just give a value to the numerator. Put it to 1. If you put that to 1, it's always true, right? Because A 1 to 0 will be less than 1 then, right? Would you agree on that? And that's the simplest Metropolis algorithm. You can actually show mathematically that this is more efficient than giving this A another value. So you could always make it so that this A is larger, but you just put this A0 equal to 1. Because then you know that this is smaller. It has to be. So you put it to the maximum value, and then the reverse process has to be smaller than the maximum value, because now you're going from 0 to 1. Now, what happens if I only make this kind of moves? So obviously you want to reach the largest probability. Nobody wants to be in the smallest probability. But what happens when I evaluate an integral and I only accept moves to larger probabilities? What happens after some steps? Where would I end?
You converge.
Yeah, I converge to one point. So if I do this, if I only accept moves to higher probabilities, gradually then I will be stuck here. So suppose now that you're evaluating an integral with that probability. So you're doing some integration and your probability is on P of X and you want to calculate this mean value. And then we are obviously approximating this with 1 over n. And then we are actually having x of I here, I equal 1 up to n, the number of Monte Carlo cycles. So if I now just move on to higher probability, if I only accept that, suppose now that to evaluate that integral, you need, just to give an example, 1,000 integration points. And it takes you only 10 steps to move from a random position here to there. And you do 1,000 Monte Carlo cycles. It means 10 of these Monte Carlo cycles will be different from this one. But then the rest will just be given by this point here. So that means that when I evaluate the integrals, I will have 10 points which are different from this one. That will definitely give me a wrong value, right? So I have also to accept the possibilities that I can move away. So that means I could move to x2 here. In that specific case, this one, then W2 divided by W0 is less than 1. So what do I do then? Then I have a probability ratio here, where I then say that the denominator has to be larger than the numerator. I put the denominator to the largest value 1, and this one to less than 1, because then I'm just reversing the situation. So if I collect everything, the simple metropolis algorithm in that specific case is now as follows. So what I can do then, when I look at this specific ratio, I can simply say that this A of j goes to 1 is equal to the minimum of 1 and Wi over Wj. So what I'm doing then is if I take Wi over Wj larger or equal than 1, this is equal to A of j going to I, and A of I going to j. I'm simply putting this one to 1. Period. If I have Wi of Wj less than 1, less than 1, which is then equal to A of j goes to I, and A of I goes to j, I'm simply putting this one to 1. So the metropolis algorithm then, simply if I want to translate this number which, or this quantity which we have here now, this expression here, into an algorithm, this is very easy to implement, the metropolis algorithm. This is the metropolis. So let's just write it down here. And this is the last. So this is the metropolis algorithm. Metropolis sampling algo. So the way you would implement it, you pick a random number. number R from a uniform distribution between 0 and 1. This is the simplest possible way. And then if R is less than equal than Wi divided by Wj, accept. So this is the way we accept the move. And then we are guaranteed that we will move to regions with low probability, but we will also move to regions with high probability. Or we can stay in the same spot, because that is also an observation. Yeah? You would typically use a uniform distribution. That's the common. So R is given by the uniform distribution. So you pick a random number, and many people, what they do is actually they look at the values of Wi and Wj, and then you can actually, instead of testing it for all cases, you could only test it for the cases where you know that Wi, Wj are less than 1. Because if it's larger than 1 or equal to 1, you always accept. So you always accept a move to higher probability. You always accept staying in the same spot. But then you have a condition on a move to a lower probability. So it's this simple. So you don't know anything. We started with not knowing the transition probability. And now you have a way to simulate your lack of knowledge. That's essentially what we are doing here. Because what we know is the ratio between the probabilities, because we have a model for the probabilities. Yeah?
But we assume W is Gaussian.
Yeah, in this case, but in general, it's our wave function squared.
Oh, okay.
So when we simulate, it's our wave function squared. So that the Gaussian was just as a simple example, because the intuition tells us that we will obviously move to higher probabilities. But if we do that, this normally takes few steps actually. And then you will just be stuck there. You won't move because there is no higher probability, right? So if you've done statistical mechanics, this is the same as you moving to the state which has the lowest energy. So just to give you, this is a small digression, because when you do statistical mechanics, the probability of being in a state at a given temperature is given by E to the minus beta, the inverse temperature, multiplied with the energy of that specific state, divided by the normalization constant, which is the partition function. The beauty of statistical mechanics is that you can derive everything from the partition function. So I remember to me, statistical mechanics is one of the most beautiful parts of physics. So I remember when I was a student, we had a course in chemistry, which was the first course we had. And we got all these thermodynamical relations like Gibbs free energy, Helmholtz free energy, etc. And we asked the teacher, what do they mean? Just a formula, use it. That was very dissatisfying. And then we started with statistical mechanics, and you could derive all this expression from the partition function. But the partition function is a difficult object. It's a normalization constant here. And it's a multidimensional object, which is almost impossible to calculate. And the nice thing with the Metropolis algorithm is that it always takes into account the ratios. So in statistical mechanics, you would obviously, at a given temperature, you would converge or move to this situation with highest probability, which then corresponds to the energy of that specific temperature. And if the temperature goes to 0, it will be the ground state. But now we are dealing with a quantum mechanical wave function, which then depends on spatials and spin coordinates, etc. But the principle is essentially the same. It's the ratios of probabilities which we are evaluating. And this is the simplest form of the Metropolis. Later, we are going to guide the jumping according to the probability distribution. And then we will have a model for that transition probability P. Now we just assume that the process is reversible, which means that we're saying that the likelihood for moving from I to J is the same as going back again. That's the metro. And this is it's so, if you think of the results which I showed you with the harmonic oscillator, you're getting spot on the energy. So this is what we are going to start with now. Now you guys need a break. Alexander is also coming, and he will be with us during the exercise, the lab sessions. Any questions before we take a small break again? Okay, let's do a small break.